this is work I'm very pleased with, I should say. But I find, if it's not already apparent, I find it very difficult to talk about this work. And the reason for that, I think, is that I like to, when I'm talking to other people, to an audience, I like to talk in terms of pictures and ideas. But this work involves formulas in a way that you just can't escape. And formulas are usually something I'd like to do in a closet alone. All right, but I have to get them out there in front of you. So bear with me, please. All right, so where are we? Let's bring this up to date. So I have a rational map. And let's just say my goal for this rational map is to show that its first dynamical degree is transcendental. Okay? So it's the rational map has a particular form. It's a monomial map composed some birational factor, which is not monomial but somehow good on toric varieties. That's most of what we need to know at the moment. And last time where I ended up was in the following place. If you have a line in projective space, and whenever you take a forward image of that line, you have some kind of avoidance condition. Okay, so all the forward images of L miss the indeterminacy set of the birational factor, which essentially that's the indeterminacy set of F. And all the forward images, they can't miss the exceptional set. They can't miss the contracted curves, but at least I can require those intersections to be inside the torus. Okay, if that happens for every n, then I have this way of associating just sort of finite sums of point masses to curves. And if I take the measure I get for L, then that relates to the measure for f to the n of L according to this formula. Okay, so I push the measure for L forward n times, and I add this correction, which comes from intersections with the exceptional set. Every time an image hits the exceptional set and you map it forward again, that point maps out to a pole, and that pole contributes to this measure here. Okay? Oh, and there's a mistake. See what I was saying about formulas? That's an A, not an F. So this extra measure mu in the correction term is again finitely supported measure on RD, and it consists of integer vectors that index the poles that contain the images of exceptional hyperplanes. It's a lot of information to take in, but we have this formula. Okay, so maybe last time I had 3 minutes left and I stopped, and I sort of regret not going 3 minutes longer because now if you take this formula, integrating the support function per psi infinity against, there's going to be a lot of formulas that I label. Okay, so this is complicated, so I'll label it with an exclamation mark. Integrating the support function for the line at infinity against this formula gives what I'm really interested in, and that is a formula for the degree of f to the n. Every time I integrate the support function against the measure, it gives me the degree of this curve. So the degree of f to the n of L is really just the degree of f to the n. The degree of that thing, that's really just keeping track of the degree of the nth iterative of the monomial map. Okay, and then similarly with the correction term, you have, again, degree of f to the j. Did I put indices on my sum? Yes. You have sum from j equals 1 to n, degree of f to the a, and then you have whatever you get when you integrate the support function against this thing. So in the paper with Mattias, Jason and Holly, we just called that capital psi of, and we think of it as a function of the matrix that we're using here. So where I'm going to write this out one more time. Let's just do this for A. This is just short for this integral, and this integral, if you unwind it completely, is, what do we got here? Some V max of U in some other finite set of vectors, product of A, V, and U. Okay, so I got a formula for the degrees of f to the n here, but if you think of these degrees, if you take generating functions, if you think generating functions instead of individual n, then you get a much simpler formula. So i.e., just to use the first letters of the alphabet here, a of t equals b of t plus the sum, plus a of t, c of t, where A, B, and C just package up the various pieces of that formula. Well, I can leave the goal. So A of t is the generating function. Let's use J's. For the degrees of f. B of t is the generating function for the degrees of HA. And C of t is equal to, well, the generating function for this capital psi thing. So some, only this one starts at 1 because that sum starts at 1. There. And each of these generating functions, you can say what the radius of convergence is. Why? Yeah, because I shouldn't write degree. Yeah, thank you. Okay, the radius of convergence of the first series is the number I'm interested in, or 1 over the number I'm interested in. It's the dynamical degree of f, if you think about it. And the radius of convergence of the second generating function is the degree of the monomial map. And I have a particular, okay, so now it's time for me to remind you about my A, all right? My A, I want, the most important thing about A is I want it to have a leading pair of complex conjugate eigenvalues, and I want the arguments for those eigenvalues to be irrational, all right? In dimension 2, it's very explicit. You just take zeta to be some Gaussian integer, and capital A is the matrix for multiplication by that integer. In higher dimensions, A is some integer matrix invertible over the integers, and lots of other conditions, which I will omit for the moment. Okay, but because of my choice of A, the degree of HA is just the magnitude of that complex eigenvalue. And it turns out that it's the same here. So, okay, you have the same radius of convergence for each of these two series. This, I don't claim it's obvious just looking at this, but it's true. And it's not difficult. You just, as I say, shut yourself in a closet and compute, or think about it. Right, and then another remark here. When d equals 2, the psi, so when d equals 2, there's a nice coincidence. So v is equal to what I was calling p last time. So these are the primitive vectors generating the rays. In the fan of P2. And what that means is that only in dimension 2, this psi is again just the degree of the jth iterate of the monomial map. So in dimension 2, you have 3 power series, A, B, and B minus 1 right here, because this one's missing a 0 term. All right? Okay, and as time goes on, not far into the future, I'm going to limit myself to the picture in dimension 2 because all of the ideas are already present. All of the ideas I can possibly expose today are already present. And, but formulas are a little bit nicer in that case. Okay. I'm just doing, this means I want to think. Yes, right. Okay, so let me rewrite that formula. A of t is b of t plus a of t ct, so this is the same thing, I think, as that formula, right? Okay, and if you look at these series, they're all, as a function of a real variable, all the coefficients are positive here. So for positive t, these things are like strictly increasing on their domain of convergence from wherever they start to infinity, all right? And what this formula means is that a of t is blowing up when c of t is 1, okay? So this implies, so where does a of t blow up? When you hit the radius of convergence. So lambda of f inverse is the place where the denominator is 0. So t equals lambda of f inverse is lambda of f inverse is the unique positive solution of that equation. Okay, that's my power series formula. And I'm not going to keep calling this C of t as time goes on, so let me just write it out one more time. Since we're starting at 1, this power series starts at 0, and it increases to infinity, so there is one solution there. Okay, so this is kind of where I hoped to end last time. But so be it, we're there now. Okay, now, so I want to show something about this formula. So in fact, we have the following theorem. So given the right choice of A, and again, the right choice of A in dimension 2 is what I wrote down. The right choice of A in dimension 3 starts here and continues with a list of 4 other conditions on A. About 4 other conditions on A. Modulo that, the theorem is that for every t positive and in the domain of convergence of C of t, so what's the domain of convergence? It's this. If you take t to be algebraic, you have C of t is not algebraic, okay? This theorem may or may not look familiar, but it is in the long tradition of other theorems. Like, if you have a transcendental function, like the exponential function, you exponentiate an algebraic number, what are the odds that you get another algebraic number? Not large, okay? And this is a version of that theorem. And why is this transcendental? Well, because this quantity here, just these coefficients don't satisfy any linear recurrence relation. If this were a rational function, these coefficients would satisfy a linear recurrence. So that, level 0, that was originally the way we started to think about this. Okay, so that was the starting point for this project. Okay, so from now on, okay, but in order to prove it, I'm going to reformulate C of t in an essential way. The idea behind the reformulation is this. Okay, the coefficients here, they just grow as j increases. So there are infinitely many different coefficients here. That's not ideal because if you look through the transcendence literature for theorems about values of power series, what you find are, if your power series has the coefficients are all 0 and 1 and some other conditions, then plugging in algebraic numbers gives you transcendental numbers. Okay, but so you want the coefficients to range through a finite set. And that's why, essentially, I want to do some kind of reformulation here. This is the moment where I'm going to drop to dimension 2. It's just simpler to write down. So just do this. So in dimension 2, what do we have? We have C of t is the sum from j equals 1 to infinity of the degree of ha to the j, t to the j. Now, how do I get these coefficients down to a finite set of values? You remember that the degrees grow like zeta to the j. So you give and take a zeta. Okay? So this is, okay, so the other thing, before I write the next line down, the other thing is these degrees, they really only, so they involve a max over finitely many things, all right? And where is that max? Where did I put it? Right there, thank you. If you look at that maximum, which vector u maximizes that inner product, what's important about AV is not the magnitude of v. The magnitude of v is irrelevant here. It's only the direction of v. Okay, it's only which direction. And in dimension 2 especially, but higher dimensions too, how does A affect the direction of v? It's just multiplication by zeta. All right, it's really just a function of the argument of AV. If in dimension 2, AV is a vector in R2, you think of that in polar coordinates, and it's the angle of AV that's important here. So keep that in mind as I write down this next expression. Okay, so this, after some fiddling, is equal to what I'll call gamma of j theta. I want to use z to the j. So z is, of course, t zeta. And gamma j theta is this. But I want to write down what you find out about gamma when you compute. Have I used the word where on this board yet? We're going to think of gamma as a function just of angles here. So gamma is a function from R into, well, actually, in dimension 2, It only takes Gaussian integers for values. It only has 5 values, in fact. I looked those up. They're simple numbers, but I don't have them at the like 2 plus or minus I, 1, and some other things. Okay, it takes 5 values. It's a function of angle, so normalized angle, so it's definitely periodic. Well, it takes 5 values. It's piecewise constant. With with discontinuities. At angles phi that are multiples of 1/8. Not all multiples of 1/8, just 5 multiples of 1/8. I can write them down. This I remember. So this is 1/4, 3/8, that I could remember it. 5/8, 3/4, oh, and 0. Okay, those are the discount. So we have this sort of picture like this in the plane, and as you take powers of zeta, make this ray a dashed ray, you get points in the plane, and what happens with gamma, or this is phi, say, the argument for the point, and what happens is gamma takes a value depending on which sector phi is in here. Okay, and one last condition. The real part of gamma of phi, zeta to the j, remember that all this came from something involving maximums here, okay? So how that percolates through is that this is maximal when phi is j theta, okay? I don't claim this is all obvious, I'm just asking you to trust me for the most part, trying to make it sort of believable here. Yeah? I'm saying okay, I forgot something. There's a real part here. Yeah. Now they should be equal. Was that what was bothering you, that one side was real and the other one was not? Well, I believe I'm claiming that once you divide this by zeta to the j, it doesn't take infinitely many values. I hope I'm right about that. Okay, I'm going from memory, which is unreliable at best. Okay. But it's correctable, even if there's a mistake here. Okay. Okay, what have I done with my friend? Here. Okay, so this is now my reformulation, but now my goal becomes if z is t phi, where t is, as before, algebraic number in the domain of convergence of C, then oh, I forgot to give this a name. This is going to be f of z. Then f of z is not in Q bar. In particular, it's not 1. Here. Okay, so this, and I didn't maybe make this clear. implies that's transcendental. Okay, so now from here on, this is what I'm up to. There's no more geometry, all right? From now on, it's just an exercise in diophantine approximation, all right? There's not much in the way of pictures to guide us anymore, which means I need to look at my notes. Right. Okay. New idea. Okay, since theta is irrational, there exist integers n, integers n, such that n theta is almost an integer here, since theta is irrational. Almost, but not quite. Okay, and what I'm referring to here is just really precise in the theory of continued fractions. So we have a sequence of continued fraction approximations nk over mk of theta, other way around, mk over nk, whose salient properties are that, first of all, nk theta minus mk is less than or equal to 1 over nk plus 1 over the next convergent denominator here, okay? So certainly less than 1 over, the denominators are strictly increasing, so this is better than saying nk here. And if you just pick some other rational number and get the same nice estimate, with a, I don't want to say this, n is equal to nk, or n is bigger than the next convergent denominator, right? So you really can't, this thing is optimal among denominators in its range here. All right, so this is the kind of thing I want to do. Okay, and then for such n, the trick is going to be, where's my formula? To take this formula and approximate it by a rational function. And what I'm going to do with this rational function is, for the first n coefficients, I just leave them alone. But then after that, I make the coefficients repeat. I just force them to just repeat n periodically after that. And then I'll get a rational function, and it'll be a really good approximation of f of z. All right, where's my eraser? So I'm going to let fn of z be the sum, or for such n. I'm going to let Fn of z be the sum from j equals 1 to infinity of gamma of j tilde theta z to the j, where j tilde is always between 0 and n minus 1, and is chosen to be congruent to j mod n. Okay? If I do that, I can even write down which rational function this is. It's 1 over 1 minus z to the n times the sum of the first n terms in the power series for f. Okay. That's right. So let's assume at some point I needed to say this. I haven't explicitly said it anywhere. So assume, I don't actually need this just yet, but it helps me explain the idea. Assume henceforth, to get a contradiction, that f of z actually is in Q bar. Okay? So all these gammas are Gaussian integers. They're in Q bar too. So certainly Fn of z is in Q bar. And now the idea is, okay. It's actually twofold. The first thing sounds innocuous, and in dimension 2 it mostly is. First of all, Fn of z is not equal to f of z. And that's the sort of thing you think, well, of course not. I mean, you know, one is a rational function, the other one is not a rational function. But, you know, for random values of c, they could be equal, okay? But I have, where is my maximization condition? This one right here, this maximization condition. This forces it to happen, all right? So I'm trying to create good approximations of f of z. I'm trying not to get f of z itself here, okay? And the second part of the idea, which is where all the rest of the work is that this difference is going to be implausibly small. All right? So don't think algebraic numbers, think rational numbers. Okay? If f of z were a rational number, it would have a fixed denominator. All right? And you ask, how close can you get to this rational number before you equal it? Well, not too close because of the denominator of f. There are limits. That denominator of f sets limits on how close this can be. Okay, and you hope for algebraic numbers there's a similar sort of thing going on here. Okay, now so for a couple of technical reasons, I'm not actually going to directly work with f of z minus fn of z. I'm going to work with, I'm going to multiply it through by something to clear denominators. So I'm going to consider what I'll call en of z, what we called en of z, which is what I get when I multiply through my two real part f of z minus fn of z by 1 minus z to the n. Okay, so yeah, go ahead, Serge. F of z is the sum before f. Yeah. Right. Thank you. Thank you. Like that? Mm-hmm. Mm-hmm. I'm assuming f of z is algebraic, so the whole pile here is, I'm assuming to get a contradiction, so this can be algebraic too. Yeah. Oh, because of the real part? Is that's bothering you? No. Uh-huh. Oh, but that doesn't, if f of z is transcendental, the real part could still be algebraic. Yeah, I see what you're saying. I see what you're saying. And do I see the way out? That makes one of us. Okay. Serge has it. Talk to, yeah. Yeah, okay. Yeah, yes, absolutely. Not off the top of my head. Right, if you have a power series with huge gaps and you plug in. Oh, if you have too good of a rational approximation. Mm-hmm. Mm-hmm. A polynomial and yeah. Yes, yeah, it is that sort of idea. Right. Yes, yeah. That's it. Thank you. That's the piece of it. Right. So the absolute value bounds the real part. Yeah, that's it. Okay. So as I said, I'm going to clear denominators here. I'm going to clear the denominators of fn of z. F of z is a power series. Okay, so when I say clear, I'm going to clear denominators in this thing. Another nice feature, that's one thing I want to clear some denominators, but another thing that's just kind of convenient that pops out of here is that, what is this? You do some computation, a nice exercise. You get a power series that starts with n plus 1. And what are the, okay, well, it's a power series in z. This is, again, there's a real part here, 2 real part. And what are the coefficients? They are the old coefficients, but the jth coefficient minus the j minus nth coefficient. Oh, I haven't got it. Sorry, I forgot something in the formula. I need a new line. This is 2 times the real part of 1 minus z to the n bar times the sum over j greater than n of gamma j theta minus gamma of j minus n theta z to the n. Takes a bit of effort, but not terrible to go from here to here. And what you expect is, okay, so how are you getting from this coefficient, or how are you getting from this gamma to this gamma? You're just subtracting n theta from j. But n theta is about an integer, all right? And gamma is one periodic. So this should be 0. I mean, most of the time, this should be 0. So usually 0. If your n is some huge convergent denominator here. Okay, and I'll make that into a definition. J greater than, I guess this thing starts at n, so I need j greater than or equal to n plus 1 is n irregular if that's not 0. All right. Oh, not 0, yeah. I thought it. Okay. Now here, I want to harp on the polynomial nature of En again a little bit, but I'll come back to that point. Let me just continue this train of thought. The proposition is that there exists a constant. Let's just use a little c, even though I've used little c once today already. There exists a little c bigger than 0 such that all the j's between nk and nk plus nk plus 1 times the constant c nk plus 1 are all, not n irregular, are all n regular. Okay, so my power series starts with nk plus 1. Nominally, I'm saying it actually starts with cnk plus 1 here. Okay, the beginning of the power series just disappears in this case. All right, and C's not a mystery here. C is something like, you can be completely explicit about C. C, I think you can take it to be something like 1/16 in this. And I will give you the idea behind the argument for this thing. What can I, lost track of where I'm at. Here. What's the idea behind the proof? I need this picture. What happens, yeah, is regular, yeah, so not irregular, yeah. What did I say, 5 letters? Okay. So what happens, let's say you've got j theta, okay? And then you've got j minus n theta. N theta is nearly an integer, so you can barely tell the difference between j theta and j minus n theta. If they happen to fall in the same sector, So I'm drawing this picture for an n regular j. If they're n irregular j, the picture, I have colored chart. Somebody, was it Julia who was using color and then said, hope none of you are colorblind? I'm your guy. Okay, so if you're n irregular, the picture is actually this. Or vice versa, this. So j minus n theta. That's the picture for an n irregular j. Okay, now there's this total coincidence in dimension 2 that these angles are all rational angles. They're all multiples of 1/8. So I can just multiply this whole picture by 1/8, and then I have more colors. Green. Right, I absolutely could not distinguish these, but okay. If you multiply this by 8, you have 8j theta and 8j minus n theta. They straddle 0 here in the angle, which means if you take the difference between these things, this implies n is what? Or 8n is bigger than something like nk plus 1, or just to be safe, let me say 2nk plus 1. I'm not quite sure, so I'm just going to put a 2 in there. Okay, at any rate, n's got to be huge for this to happen because of the sort of optimality feature of mk over nk. Okay. Yeah, so this has to happen, and that forces n to be bigger than this. Yeah, I'm doing something wrong now. Oh no, it's going to force j. I think it's going to force j to be bigger than this, which means you're outside an interval like that one. All right, so that is the idea here behind this proposition. And the upshot of the proposition is that if you look at this quantity, these, what was it, En of z, then it's smaller than some constant times maybe there's a 2. Yeah, no, it's fine. The 1 minus z to the n squared doesn't contribute here. So you get a very good upper bound for this thing, given that when I clear denominators, the degree of this, well, as a rational function, the degree is only nk here. Okay? So even though that degree is nk. All right, so this seems too good to be true. What we need is, we got an upper bound. We need a corresponding lower bound. To contradict this. Okay, i.e. something like you can dream. En of z is greater than or equal to some, maybe absolute value z, maybe just some other real number, but to the nk itself, or actually in the end I'm going to get, well, no, the 2 won't affect a thing. So some other real number to the nk. Okay, here you got an upper bound of the form with an nk plus 1 exponent, a lower bound with an nk exponent. That is not an immediate contradiction, all right, because R and absolute value Z may have not much relationship. They're just sort of independent of K. But for most irrational numbers, something wonderful happens. All right, so let's say it this way. Most theta in irrational, like as in almost all, are, Jason got to pick the term here. So he picked one that number theorists like. Well approximable. If in complex dynamics, everybody would say unbounded type. i.e., the sequence nk plus 1 over nk has no upper bound. Okay, that's fantastic because now I have this estimate. If I can also get an estimate like this, and I assume my theta is well approximable, then you're going to get your contradiction out of this. Okay, so I don't have this estimate yet. I need to argue for this. So this is a double exclamation point. Yeah. T times zeta. That's right, right. The important thing about T times zeta is T is algebraic and real. And so zeta, what's important is T zeta has the right argument here. Yeah, shares an argument with zeta. I don't think you've been able to ask your question yet. Z is fixed. Z is fixed. Yeah, I have, yeah. In my mind, though, it's important for me to just think of it as Z and not 2, something like that. Okay, so if this is unbounded, so this implies, so corollary, double exclamation point, and theta. Well approximable implies contradiction QED. All right. But these are both assumptions. Concerning these assumptions, okay, I said almost all irrationals are well approximable. We don't have much choice about our irrationals. Coming from a countable set of their arguments of algebraic integers, all right? It's coming from a countable set. So we don't know this, which is very unfortunate and irritating. I mean, because you're like, you know, something that is much of the end of the argument involves various sort of super implausible things that you need to rule out. And it somehow offends that you have to spend so much time dealing with things that, you know, on another day you'd feel like you won the lottery if they happened. Okay, so that's one thing. And concerning this estimate, How much time do I have? 5 till 10. Shoot, I've given myself enough time to talk about it. Be careful what you wish for. I'm saying you get the estimate, but it's you don't recognize it. At least I wouldn't have recognized it when I first saw it. The actual theorem is impressive. All right. So from this point forward, I think I'd like to say something about that. Yeah. It's strictly less than 1. Yes. Yeah. Because we scaled it by zeta, or we scaled t by zeta. Right. Yeah, so this f of z has radius of convergence exactly 1, and z is in the unit disk. Yeah, unfortunately, z is no longer real, but it's not that important. Okay, I'm going to paint myself slowly into a corner here. So what to say first? Oh, I said I was going to come back to this En of z. I said, so here's a remark that is very helpful for what comes next. So En of z, what I don't like about En of z is I started with this f of z, which is great for me. It's a holomorphic function if z is if you think in complex analysis terms. And then I went and, well, the real part already spoils that. But then you multiply it by this magnitude of 1 minus z to the n squared, and it's even less holomorphic. Okay, what I didn't appreciate is that doesn't matter. It's a holomorphic function of z and z bar, and that's what matters here. So En of z, it's as a function of z and z bar, it is a polynomial of degree 2n plus or minus 1 in z and z bar with coefficients in a finite set, which I will label capital Z, I'll try to make it big, which includes, or consisting of, things like the values of gamma, that's 5 things, possibly their difference, and differences, maybe you need things like 0 plus or minus 1 just to be safe. But I'm going to create a finite set. The list of things that goes in this set is a little long, but I want to give you the idea. But if I stop here, okay, I've kind of taken care of the coefficients of Fn, but you say this can't be a polynomial because f of z is a power series in z. It's got, it doesn't stop, okay? But it will be a polynomial if I include f of z in z. Okay, so I let f of z, I'm thinking, now I'm going to think of f of z as being one of the coefficients in the series. So the coefficients include that. All right, that's good. So now what I'm going to do is choose, so by assumption this is algebraic, by construction everything else in capital Z is algebraic. So I'm going to let K be a number field that includes everything in Z, and also little z, and I'm probably forgetting something to include here. But I can only do this because I'm assuming capital F of Z is algebraic. Okay? So, and then, so I'm going to let M, well, I'm not going to let, this is standard notation. So MK is going to be the set of places on this number field. And you don't need to know what a place is very much. All you need to know is for each place, you get a nice absolute value on K. But for every nu in MK, absolute value nu be the corresponding absolute value. Okay, and I should, in full disclosure, places fall into two types. There are finitely many what are called infinite places, where the absolute value is Archimedean, like the absolute value on C. And then there are a bunch, there are infinitely many finite places where the absolute value is non-Archimedean. And to fix ideas, which I need to do in this subject, just think of K equals Q, okay? On Q, the infinite place is the one corresponding to the usual absolute value. The finite places are the ones corresponding to p-adic absolute values, okay? You can also make nice analogies to thinking of K as like the rational functions as functions on the complex plane here, okay? Infinite places being like degrees and finite places being orders of vanishing at various points, all right? So you have these places, and for my purposes, there are two important things to know. First thing is you fix a point in K, and for most places you get 1 for absolute value. For all but finitely many places. Okay, this is like saying the zeros of a rational function are a discrete set. The other fact is the product formula. If you multiply, so now this makes, in light of 1, 2 makes sense. You can multiply together all the absolute values over all the places, and you get 1. This is kind of like saying, you know, poles minus zeros is degree or something like that. All right, for a rational function. That's not quite true. Never mind. So these two features, and I wish I were done with the definitions, but I am not. Okay, so now I need to do, in order to state the Aversa result that I'm going to state, did I mention that? Yeah, I haven't written down the name Aversa yet. In order to state the thing that gives me this, I need to then use 1 in order to single out the sort of active places for this number field. So it's be a finite set, be the finite set of places such that the absolute value of x nu is less than or equal to 1 for every x in z union little z. And again, I'm probably forgetting to throw some other things into this sink. And for every place not in S, okay? This is a finite set. You just throw in all the infinite places because you can and because you need to state the theorem. Okay, so you have a finite, is this? Oh no, it's, yeah, wait, I've got the wrong definition here. Give me a sec. Nu in S, I'm thinking of something else when I wrote this down, implies x nu is not equal to 1 for some x in Z union Z. At this point, this is something I care about probably much more than the rest of you do, but it's some nice set of places, and I'm going to let OK of S, which is called the S integers, be equal to the set of x in my number field such that x nu is less than or equal to 1 for every nu not in S. Okay, this is the moment where I care most about this observation here, that En is a polynomial. So because of the way I set things up, yeah, I can lose this now. Fact, all polynomials in Z bar with coefficients in capital Z are S integers. In some sense, these are the only S integers I care about now. But this is why I needed polynomials. If I had rational functions in Z and Z bar, it wouldn't work. Even rational functions in Z, it would not work. Okay, what's even better, and I probably won't get to this point, monomials, or let's say capital Z monomials, in Z bar are invertible. In this ring. So that means that over here, I don't have less than or equal for all nu not in S. I have equal for all nu in S. So if I do this for a monomial, it's even better. Right. Now I can state Iterates' theorem. I want to put it somewhere where I won't regret erasing something. I'm not going to state the most general version of this theorem, but I think once you see this, you'll be glad I didn't include any more. So in this context, what I want is the following. For every L and epsilon, and any S integers, x1 through xl in OK of S, we have an estimate on the sum, right? And the estimate, what do I want? I want my inequality to go this way, and this theorem has this. For any, there exists a constant such that there exists a constant such that this is greater than or equal to a constant. I should have a square here times the maximum of the xj squared. This looks great for my purposes, okay? My En is essentially a sum of two things. I should just take L to be 2, and I should add the two things together, and whichever one is bigger gives me the lower bound here. But there's more. Okay, there's a denominator, which is unfortunate. Okay, and the denominator includes the epsilonth power of some kind of height associated through x1 through xl. Okay, and because of the epsilon, I'm not even going to tell you what this is. All I'm going to tell you is that I can tweak the epsilon to make it irrelevant. Okay? And the other piece is it looks like I'm taking the product formula again. So you get product from j equals 1 to L. That's not the product in the product formula. But then you take the product of all the places in your set S of xj nu. Okay, so it's a truncated kind of version of the product in the product formula. And I stress that it works against you because these things, you're taking places in S, these things are, and you've got S integers. These things are all going, they should all be greater than 1, I believe, here. I have this going the right way? Anyhow, yeah. And then there's one more condition. So we have this provided x1 plus dot 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 plus xl isn't degenerate in the following sense. It has no vanishing subsums. Okay? So what do I mean? I mean there's no finite subcollection of the x's that add to 0 here. In particular, the whole thing doesn't add to 0. So if these things perfectly canceled out, of course you would have no lower bound like that. But I'm asking for more. I'm asking like each of the things individually cannot be 0. That's not so serious because if one of them were really 0, you just exclude it from the mix, okay? More seriously, you can't have like the first, k of them add to 0 and the last k don't, because the first k of them could include the one that has the maximum right here. All right? Yes. Yes, when I write without a v, I'm using the absolute value on C, which is corresponding to one of the places, but yeah. This really rankled Holly. She does not like to think of her numbered fields embedded in C. What about that? You can take the epsilon to be anything you want, but the constant will change with epsilon. And the idea is the terms are both bad for the estimate. The terms in the denominator both make things worse because they tend to be huge, all right? This one tends to be bigger, but the epsilon helps you, okay? You can use it to kind of cut it down to size. Does that make, or is that your question? What's that? It's because it's because I added this layer. Yeah, right. For every L, for every epsilon, there exists a constant, depending on L and epsilon. Yeah, it's the quantification is just out of, yeah. I mean, when you look at this, you feel like maybe I'm about to break out estimates on a PDE or something. It's just really, I find it intimidating. I mean, like, I look at this and like, I ask myself questions like, what if you multiplied everything by 3? What effect would that have on the estimate here? I don't know. I mean, it's the denominator is a mess. But you can come to suitable terms with this thing. All right, so now, just crude estimation. For fixed L gives that the denominator, or it gives an R greater than 0, such that the denominator such that if x1 through xl here are z polynomials in my little z and little z bar, then how to say this? Let's make this a capital R. Then the denominator is less than or equal to, I forget exactly, R, we'll just say R to the n, where n is the sum of the degrees in the xj. This n is what gives me the nk in this estimate right here. All right? The estimation is really not bad. I'm pretty much ignoring this term. There's probably there should be sort of like an n plus epsilon here. How about if I just put it in there? Okay, but that's not very serious. Or maybe it's n times 1 plus epsilon, something like that. Right, and so this implies after some work that the estimate that I want right here. Okay, so that's almost enough about that. Okay, so I want to conclude then with 2 further things. I said that my theta was not necessarily well approximable. This entire discussion was predicated on theta being well approximable. Okay, so what changes? What changes when theta is not well approximable is I don't have this proposition. Okay, instead, what I have is there exists for every big C, or for, how about M for once, M bigger than 1, or well, bigger than 0, we have less than or equal to M constant times m n irregular indices in that interval, okay? So I lighten up, here I have a fixed C that I can't change. Here I get to pick my M, but now I get n irregular indices in that interval, okay? And that really messes up my En. So now I've got to contend not just with two pieces, the f of z and the fn of z, I've got to contend with these sort of leftover pieces corresponding to irregular indices, but they're all monomials, okay? So it means that when I apply Evertz's theorem, L's going to be a lot bigger. I'm going to have to, instead of L being 2, it's going to have, it's going to be something large depending on M. Okay, so it looks like this is just headed way downhill here, but because all of the things I'm adding in are monomials, all those monomials are units, so this particular quantity is 1 for all of them. So my bound for this thing, which is the main part of the denominator, does not get worse for those monomials. All right, and that saves everything. I mean, there's substantially more to this, but that's as much as I can say. So now, that's it. That's the end of the proof of the transcendence, as much as I can give. I want to point out that there's been some developments since our papers, which are very nice, and I wish I knew all the details, but at least I can mention them. Okay, so Sugimoto improved on our results in 2 ways. Okay, so he proved theorem. There exists a rational map F from P3 to P3 with lambda of F transcendental, same theorem so far. But he can show that his lambda is the largest of the dynamical degrees of F. So maximal among, well, here, I guess lambda is, remember I was calling it the first dynamical degree. In dimension 3, there's 2 others. One is the topological degree, but it's birational. So the main thing here is it's bigger than the second dynamical degree, okay? In the specific examples we have, we either didn't have it or didn't know if we have it. So he could prove that, this is, that the dynamical degree you usually care about is the largest one. All right, and then he went on and more recently did something very nice. For every d greater than or equal to 6, there exists F such that lambda 1 of F through lambda d minus 1 of F are all the dynamical degrees are transcendental. Which surprises me because, in general, I don't know how to get a power series formula for these other dynamical degrees. So this is, he has a nice trick that I'm not qualified to recount. Okay, so that's Sugimoto, and the other is, is it Matsuzawa? That's terrible. I'm not remembering names. Yeah, Matsuzawa and Long. Okay, so theorem. And I think this is heavily using some work of Gia, but I'm not up on these things. So for F in Sugimoto's first theorem, we have that alpha of F, which is, sorry, what's the name? I'm blanking on the name of this number. What's that? Yeah, the arithmetical. Dynamical degree of F is also lambda of F, which means that this thing is in Q bar. I'm not going to define arithmetic degree. It's for maps defined over Q bar, and there's some conjectures of Kawaguchi and Silverman, of which, you know, this is one instance here. But the expectation is if you have a map over Q bar, then this arithmetic degree is the dynamical degree when the first dynamical degree is largest here. And they prove it for a class of maps that include that one right there. So this thing can be a transcendental number. What's that? Not in Q bar. Thank you. Yeah. I really appreciate you guys staying on top of me like this. Very reassuring to, like a safety net. Yeah, so maybe that's a good place to stop. Thank you. I did not recall the formula for G. Yeah. Yeah. In fact, G has coefficients in 0 plus or minus 1. Or you can make it that way there. So it's defined over, you know, anything but Z2 or characteristic 2 fields. Yeah. Yes, fields of characteristic bigger than 2. Yeah, right, yeah. One meaning one of you, not me. Yeah, I was happy with C, but yeah, right. We thought about it briefly. So G just degenerates to the identity map in that case. You need a different map. Oh, I wish, yeah, just one such, yeah. As far as we know, no. And since one of us is Jason, I suspect nobody knows. I mean, Jason really is, he's like an encyclopedia of knowledge about that kind of thing. That would be, you know, it's true of all mathematics that, you know, you get the impression that so much is known, but, you know, you step just a little to the left, a little to the right of what's known, and you're suddenly completely lost. It's especially true in diophantine approximation. You take any result and make a slight change and nobody has any idea. And this is an instance of that. It's on archive, it's not published yet. Yeah. Oh, they're all algebraically independent, lambda 1 through lambda. Oh, good question. It didn't occur to me. I suspect not because of the trick he played. I think they're just like products of, you're nodding. Do you know this paper? Or are you just agreeing? Yeah.